Hello, welcome to our last online meeting for MTH218. So, first thing I want to impress upon everybody, so watching or recording or etc., is to do the subject evaluation. So there's, at the end of every subject, there's an evaluation form you can do. Just pretty much you can go to any Interact2 site you want to at all and click on evaluation and you can fill it out. I really appreciate that. It gives me an idea of how things have gone, etc. And so I've certainly used it in the past to change how the subject's going. I also listen to people during the sub session as well. Well, I try to, and change some things. So please give your opinions there about various stuff. We'd like to know, and so please do that. You can do it after exam, but often it's easiest to do it now while you still remember about it. So I encourage you to do that. You can do it on a mobile device, etc. So if you're watching the recording now, pause it and try to do the evaluations before you forget. It's my suggestion. If you're watching it live, then don't go just yet. So last week we're looking at revision, and we're sort of thinking in our minds two things now. Is there's the online assignment that's due this Friday, and it's an assignment, remember, which means that you don't have to go in and finish it all in one go. So there's that. But also there's some questions in your final exam on vector calculus. So we looked at line integrals in last week and just touched on flux integrals. I want to mention a bit more about flux integrals today. So a flux integral, it's good to get a sense what it even corresponds to, is how much a vector field flows through a particular surface. That's the idea of how much it flows through, hence the name. And these vector fields, they arise in electromagnetics, for example. So these fields can be an electric field or magnetic field. We want to see how much changes through a certain region. So those sorts of things. So that's where it sort of comes from. Now, if you've got certain conditions upon the vector field, namely if the divergence is nice or the curl is nice. So in particular, if the divergence is 0, that's pretty nice. That means it corresponds to, say, an incompressible fluid, for example. Or if the curl is 0, it means an irrotational vector field. So various nice things happen. Then some of these flux integrals become very easy to work out. So if the divergence is 0 for an incompressible fluid, then it only matters, only the boundary matters in that situation. So it doesn't really matter what the surface is, and you can see sort of things cropping up at times. So there is a sense of, under nice circumstances, allowed to deform the medium as long as the boundary stays makes, and it's all okay. So there are some nice properties of which, sort of touching into, what we go aiming for this object is a little bit just a touch back from that, and then it's just being able to give various flux integrals, better work them out. So I want to talk about the methods how you do that. So first off, if you're faced with any flux integral, go for the easy methods first. And so check if the surface is closed. So just like with line integrals, checking it's closed is a nice theorem to begin with. So if a surface is closed for a flux integral, then you can use divergence theorem to quickly work it out. So let's just do one example. Of that, and then we'll show you that why you never want to do it. Oh, I would want to do it another way with this one. So, so we got a surface which is the sphere. So a big ball here. The radius 3. So we got a surface. So it's a closed surface. So as in there's no hole in it or anything like that. And we've got some vector field which is to try to draw. So I won't bother trying to draw it. And we're trying to work out how much flow is coming out of this surface, essentially. So we're assuming that it's outward facing. Normals. So that's the default. So you got to close for you assume it's outward facing by default. So there's various things to do here. So because it's closed though, divergence theorem seems like a good idea. So since it's closed, then we can basically work out the divergence of this vector field, which would be just a scalar, and integrate that over the enclosed region. So for short, say E for enclosed, integrating over the enclosed region over that entire volume of the divergence. And that normally makes it easier in circumstances, particularly because the divergence is dropping because you're differentiating to work out the divergence. Often you can drop lots of terms out and reduces the variables a bit. So often that's an easy way of doing it. So in this case, we have to work out the divergence. So again, to remember, the divergence is the dot product of the differential operators and f. So it's pretty much saying is partial with respect to x of the first term plus partial with respect to y of the next term plus the partial with respect to z of the last term. And like often happens, things simplify. So you're getting 1 minus 2x, 1 plus 2x, and 0. Lots of things cancel out, which is plus 0, I should say, plus 1, yep. And you're left with 1 plus 1 gives you 2. So the divergence in this case simplifies down to a very nice simple number even. And so our flux integral by the divergence theorem then is the triple integral over the enclosed region of 2 dv. And because that's a constant, we can take 2 out the front, and it's just the triple integral of just the volume. So that would just be the enclosed volume of the enclosed, the volume of the enclosed solid. And since it's just a sphere, we know volume's a sphere, so volume of the sphere is 4/3 pi the radius cubed. And since it's 3 there, the radius is 3, and that will give you pretty much the answer. So 2 times 4 is 8. 3 and 3 cubed gives you 9. So it'd be 72 pi. That's our answer. So the divergence theorem in this case worked really nicely. So whenever you've got a closed region, it's always a really good thing to do. I'll talk about what you would have to do if you couldn't do that in a second, and not actually do the whole process, just to show how time consuming it is. So that's really helpful. So if the vector field, if the surface is not closed, then you have to do something else. So the next sort of thing you can do is if you're doing a vector field where you've got where the vector field is actually a curl, just like here, so double integral of curl or something, then that sort of reeks of the sort of pattern that Stokes' theorem has. And so when you've got that situation, then using Stokes' theorem is a good first step. You might need to do some things afterwards. Indeed, this is sort of a special case, actually, is when the divergence of whatever's whatever the vector field you got here, if the divergence of that is 0, then nice things happen, actually, is the more general situation, which normally is a more advanced method, I'll touch on briefly. But normally when you see that, you're thinking Stokes' theorem, and that's a good first step. So let's just do an example of this one. This is another one, a question from the sample exam. So if you're asked to do this flux integral here, integrating over a bit of a paraboloid, so let's draw a picture here. So the paraboloid, it's a circle at the xy plane, otherwise sort of paraboloid like that, so that's basically what the picture is. So in the bits of the paraboloid below the xy plane, and it's oriented downwards, so let's just put an arrow here, so that's the normal pointing down. And then we have a vector field f equals x squared plus x y. So which would be, you could draw if you wanted to, but let's not colour the picture. So that's our different paraboloid. So we want to work out how much of this vector field is flowing out of this region towards the bottom, towards the bottom. Now, because there's a curl there, you're thinking, oh, that really sort of makes it look like to try to use Stokes' theorem. So Stokes' theorem states that if you've got the double integral of a curl, that's just the vector line integral around the boundary. So it's the boundary of P of f dot dr. So via Stokes, you pretty much convert it to the boundary is just that circle. Now you have to be careful with the orientations here, something really worthwhile specifying, and that is to work out the orientation of the surface, which is pretty much the direction of the normal, induces an orientation on the boundary, and you have to work out what it is and make sure they match up. And the way to do it is just right-hand rule. So you stick your thumb in the direction of what normal is. So put your thumb down, and then get your right hand, and then your fingers on your right hand curl around that way. And that tells me that the orientation of this circle, looking from above, will be clockwise, which is different to normal. Like normally you expect anti-clockwise. Now the reason is because it was oriented downwards, and therefore you get opposite to what you might normally expect. So basically, Stokes' theorem allows you to do this a vector line integral around this particular circle, and that's the boundary of the circle. And you can write that down if you wanted to. So that's the integral around the circle of f dot dr. If you do it, ends up being x squared plus x dy. And that's a closed integral vector. It's a closed line integral. And as soon as you see closed line integrals, normally you try to use Green's theorem, and you can certainly do it here, or since it's in 3D, actually using Stokes' theorem a second time. And so if you do it a Stokes or Green's a second time, basically you can then form the integral this time of the enclosed region. Instead of picking an awkward surface like the paraboloid, you can make a nice simple one like the disc. And then the normal for that would be the induced normal we're putting down. So they're the same. So again, do an induced normal, curl your fingers in the direction of the arrow, and then your thumb points in the direction of the normal. So by Stokes' theorem a second time, or effectively by Green's theorem, it's probably easier to write it down, this becomes the double integral of the curl of f dot ds. But this thing is nicer to work with. For a start, the curl is simpler. So the curl of f, because it's really just effectively Green's theorem, is qx minus py by this stage. There is no p term, there's no thing in front of the dx. The q is x squared plus x, so that's just going to be 2x plus 1. And the curl is times by k, technically. So because we have no dz term, because it's all in the xy plane, then the curl ends up being just the k component, which you can work out explicitly, of course, but that's one nice thing that happens here. The second thing is the unit normal, because it's just in a plane, is again easy to work out. It's just going to be minus k. So it's in the z direction, but pointing down, so minus k. And if you take the dot product of those two, you get the double integral over the enclosed region, which we call d for disk, of this thing times by minus k gives you minus 2x plus 1 dA. And again, because it's a circle, you could use polar coordinates to give the answer for you, etc. if you needed to. A cheats method, which I'm going to employ, is the double integral of x times dA gives you the x, gives you the mass times the x coordinate. So I factorize the minus sign and a 2 out, and so it ends up becoming the area times by the x coordinate of the center of mass, and then the plus 1 becomes plus the area. So using a little bit of trickery in terms of total area and x coordinate and the x coordinate of center of mass, you can rewrite this integral as this one, so not actually doing integration. The x coordinate of the center of mass, well, it's a circle. It's pretty symmetric. It's very believable to say that the average x position is going to be bang in the middle here, so it's going to be 0. And then the area is pi times by the radius squared. And so the answer is minus pi. So, back in terms of the big picture, whenever you're faced with an integral of a curl like this, then you can rewrite it into a vector line integral. Now that vector line integral will always be closed, and so you can do it directly, but what commonly happens in this circumstance, because it's already closed, is you use Stokes' theorem a second time effectively, or equivalently use Green's theorem. And what that really means is you're changing, the double application means instead of integrating over a complicated surface, you end up reducing it to integrating over a much simpler surface. So what that really boils down to is you're deforming the original surface from complicated to simpler. The thing that has to stay the same is the boundary has to stay the same, and also you have, when you're moving it, the vector field has to be well defined in all the regions you're moving it through, of course. So if it's not, well, if there's a point of discontinuity, it doesn't work. So as long as it's smooth, which is a normal assumption for Stokes' theorem, then you can sort of deform it. But that's sort of a little idea for you. Yeah. Question, I gather. Yep. Far away. Just waiting for you to type the question in. I'm saying something to fill the silence rather than anything else. So yeah, so long as the boundary was the same. I mean, in this case, so this vector field here is defined everywhere, and the curl, if you work it out, is always well defined. So this is completely smooth. So if you if you got a surface with that boundary, so like that, or to bluing out, any of those sort of surfaces, and you worked out the flux of this vector field out through this surface, through the bottom, no matter what the surface looks like, you always get the same answer. That's correct. And the reason is because the vector field we're considering is a curl. That's part of it. The bigger reason is whenever, sorry, if you got sorry, something more general than this. So if you got so if the boundary of two surfaces are the same, so you've got two surfaces quite different but have the same boundary, and then the divergence of the vector field you're considering is 0. I just said in a physical context just only means you've got, say, an incompressible fluid. So if it's just really fluid flowing, an incompressible fluid, like lots of things are, the divergence is 0. It's a common physical constraint. Then the double integral the flux through both surfaces are the same. So as long as the boundaries are the same and it's zero divergence, they're the same. And that's really a consequence of divergence theorem, technically. So the orientations have to match up. That's the tricky bit. But we're seeing this is a special case of that. So this double application of Stokes' theorem is a special case of that. And the reason being is the divergence of the curl of something is zero. So there's a bit more maths to it than this that you'd never quite get onto, and that is if you do curl and then divergence, it cancels each other out. And again, if you do the curl of a gradient vector, you get zero, which we've seen. That's just saying if f is conservative, the curl is zero. That's what that line says. So some of these operators seem to cancel each other out, which gives rise to sort of exact sequences, and there's a lot more maths behind that, and so you can work at things like cohomology of these sort of different surfaces based on this sort of stuff. So we'll be on this subject in case you start getting worried. But these sort of sequences like that start revealing more information about the surface. Okay. So some of this stuff at the end is more advanced, but it's good just to see some sort of the overall patterns. So with all these problems, just by the way, though I'm suggesting one method more than others, there's heaps of ways of doing them, and certainly evaluating this if you think about it, evaluating the original flux integral directly is annoying in this case, and I'll show you how you have to do that. Evaluating the line integral directly is not too bad because it's just parameterizing with one letter, so that's doable. So that integral as written is actually okay to do. The one on the end is easier in this particular case, but doing this one in the middle is actually perfectly fine. Okay, so if you can't use divergence theorem and you can't really use Stokes' theorem either, what do you end up having to do? Well, sometimes in simple cases you can get away with going, well, the flux integral really is the unit normal times by f, and if the unit normal's got a really easy, simple formula to work out, which is what I did just here. So that's that example. So the unit normal really was easy to work out because it's in a plane. Then I can use that approach. So if it's a plane, or so if it's sitting in a plane parallel to one of the standard axes, perpendicular to one of the standard axes, or maybe it's the sphere sort of thing, then maybe I can get away with this sort of approach. And you can see I did that in a past case. But if that fails, then you're really going to have to parameterize the surface. That's always the fallback position. So in order to parameterize, you basically work out a particular normal to the surface. Now, in general, there's formulas for it. Most of the time, you'd parameterize in terms of the x and y Cartesian coordinates. That's certainly the easiest things to do. I know those formulas exist for many other things. Normally, you just reduce to this one here. So you work out this particular special normal. It's rarely a unit. It's not normally a unit vector. It may be in special circumstances, but not normally. But the direction of it gives the direction of the normal, of course. The magnitude of it gives a correction factor for how curved the surface is at that point in time, or how not flat it is, I guess, maybe a better way of saying it. In this particular case, it's basically the conversion factor from the ds we see in our flux integral to changing it to just an integral over dx dy. So ds really is a, so if I spell it somewhat, so if the unit normal it's got three components, to n1, n2, n3. Then ds, I'm saying the wrong thing here. So if you got a vector field f ds, that actually corresponds to p dx dy plus q dy dz plus r. Get them on the wrong way sometimes. D x dz. That's not right. Anyway, maybe I'll cross it out. I've got it around the wrong way, which I've just realised. So it should be that should be P, that should be R, that should be Q. Get the letters right. So when I already write down F ds, it actually is a double integral. Is what I'm really trying to say. But I'm getting stuffing up big time here. Is that when it's right, it looks like a single letter. It really is a double integral. Really is a double integral. But so what we want to try to do is we want to make it change into a double integral, which is something we can handle. Namely, if we can change it into just a simple double integral that we're used to from earlier on in the subject, that's the way to go. And this capital N ends up being the conversion factor between the two. And that's what its role is. So it's got a special formula to do that for you. So it's not just any old normal, it's actually one that really achieves a particular purpose. The length of it, which is given just here, for example, again is a way of converting a small bit of surface area, so ds without the bowl on it, into just an ordinary double integral too. So these particular formulas are for the Cartesian coordinates x and y. They pretty much will work in all circumstances you need it. There is a formula in general, which I've used in the notes. It's down the bottom here. I've used in the notes for, say, spherical coordinates just to show how they work. But in practice, even for things like that sort of situation, or for polar coordinates, which arise more commonly, it's still normally easier just to use these formulas, and then if you need to do anything else, just change afterwards. The reason for that is these formulas are pretty simple. I mean, it's not that complicated to work out, so it's usable. It incorporates lots of things for you already, so lots of calculations already been done. Whereas if you picked a different coordinate system, you'd have to do lots of the legwork yourself, and so it just will take you longer because you don't have the N formula straight away easily accessible to you. And it's true for, say, polar coordinates, things like that. The other thing is, you know how to do polar coordinate transformations easily. Well, hopefully by this stage. Hopefully you've mastered that sort of skill. And therefore, even if you do change it, you can easily apply polar coordinates after the fact readily, because you're more practiced for that aspect. And so although there are formulas, here they are here, to change the polar coordinates in one foul swoop, remembering these and utilize them is, sometimes it's easier it's just to do those two steps, because you don't understand the individual steps easier. Because you can see here is this formula gets more complicated, and although that sort of naturally will arise when you do the polar coordinates, it's sometimes easier just to have two simple formulas in one rather big complicated one. Anyway, enough waxing lyrical. Let's just do a question. And then we'll talk about why. So this method that I'm going to do works in all the previous cases. So all the previous cases I could have done it for, but I'll just sort of explain why I didn't before. So here we've got another paraboloid. So it's pointing up this time. So it's above the xy plane. So it intersects with the circle. So it looks something like that. So it's got a radius of 2 of the base of the thinking. So in order to try to do this, it's not a closed surface because it's got a whole big opening at the bottom here. So you can't naturally use divergence theorem, or not directly at least, although that's still, in this case, not a bad, but that's an option, which I'll look at in a second. So divergence theorem indirectly is possible, but not directly. And certainly this doesn't look like the curl of anything, certainly not obviously. And so this is not the curl of anything obvious. Then you know Stokes theorem doesn't apply, and it doesn't. That's certainly not the curl of anything, even if you did the calculations. So we're going to have to parameterize it. So the basic idea of parameterizing it, you pick some letters, and as I said, picking x and y is the obvious thing to do. And if you do that, you really want to look at the shadow this surface casts on the xy plane. So the shadow it casts, in this case, would be a circle. Now, in some circumstances, like it is in this picture here, the shadow it casts actually is the base of the whole region, and they happen to coincide. But in general, it's the sort of shadow. We'll call this region B, so that's our shadow, or B for base, actually, that we've got. So our double integral of f dot ds over the whole paraboloid ends up being changing this integral to an integral of just integrating with respect to x and y, which we're more familiar with. And the way to do that is just to basically add this correcting factor, this capital N in here, to do that for us. And when we changed x's and y's, we changed the range of integration from a whole surface into just a shadow it casts. So some key things to emphasize in this formula here is I changed the region of integration. This is the shadow in general. And then I have to introduce n. And this n here, let's work out what it is in this situation. For a Cartesian coordinates like I've picked, it's the negative of z of x minus z of y, and just one by itself. And it can either be positive or negative. Both of them are possible. And you have to look at the context to work out which of the two signs it is. So in this case, we've got z at the top, so we can work it out. So zx would be minus 2x. So minus that would be positive 2x. Same thing for minus zy gives you minus, so positive 2y, and the 1 just sticks around. So that's what the normal is going to be. So it's either pointing up or pointing down, and you have to work at which one you want. So we want it to be orientated upwards, so therefore the normal is going to be pointing up, and therefore in the z direction at least it should be positive numbers, and therefore we want this component here to be positive to get the upward orientation going. So that would tell me that we need the positive case. So just some aspects with this sort of thing here is you need to take a bit of attention and work out plus or minus, and it normally just means thinking about what would happen in the z direction. In this case, we want z to be going up, therefore the positive. So that's how you work out the n, and then otherwise plug in and see what it simplifies down to. So we're integrating over the base, which is this whole disk, which we'll fix up in a second, of f, so x, y, z, dot product with n, so 2x, 2y, and 1 dx dy. And we can write dx dy or dy dx, so whatever you feel like it. So taking the dot product, we're getting 2x squared plus 2y squared plus z dx dy. Now another key thing to emphasize, whenever you do this sort of process, what commonly happens is we're integrating with respect to x and y's, but we get the other letter cropping up, so in this case z. So z's cropping up. But they're not in terms of the integral parameters, so in terms of the integrant, in terms of the differentials. Get it right one time. So we need to change that. So we know that we are integrating over the surface, so we're just parameterizing the surface. So when we see z, in terms of the parameters we have, z is given by that equation. So we're using the parameters we've got to replace any z's by the parameters present. So integrating over this base of 4 minus x squared minus y squared dx dy. So it ends up becoming 4 plus x squared plus y squared dx dy. So just recapping, whenever you've got a flux integral, when you can't use the big powerful theorems, then you basically can pick nice coordinate system. So let's pick our xy coordinate system, xy as parameters. You just change it from the integral of f ds to this capital N, where you carefully choose the sign and plug it in, and you're integrating over the base or the shadow in more general rather than the general surface. You plug everything in, and in particular, whenever you see z's, you just replace it by the equation of x and y's. Or in more general terms, you'd replace everything in terms of the parameters. Because of what you really are doing, it's just a little bit more involved. Integration by substitution is what you're really doing. So you're just substituting the z's for the parameters x and y's you have present. So where it's more complicated is how it impacts the differential is where this capital N term comes in, and that's why you had to work it out. Now we got this integrate per normally. So I always think it's important to draw on the base, the shadow at the top, because that's what you're actually ultimately going to integrate over. So that's what you're integrating over. So it's a circle, and as soon as you see it's a circle, you go, well, I would normally pick polar coordinates for that. So that's what I'm going to do. So when I pick polar coordinates, it's 4 plus, well, anytime you get an x squared plus y squared, that becomes r squared. Dx dy becomes r dr d theta in polar coordinates. And you have to give it appropriate limit. So r is the radius. So the radius, it's a full circle, goes from the origin up to the outside, which is a circle radius 2. And theta, it's a whole circle, so you want the whole range of angles. So 0 to 2 pi, say. This becomes a separable integral because the limits don't impact upon each other, and this can be spread as a product of the two. So it's integral of 0 to 2 pi of d theta, integral from 0 to 2 of 4 r plus r cubed dr, and then just matter to do the integral. So that's be 2 pi for the first one, and the second one would be 2r squared plus r to the 4 and 4 between 0 and 2. So other than the 0, you get nothing. So other than 2, you're going to get 8 plus 4 gives you 12. So 24 pi, I think is the answer. So this last bit, hopefully, is the things you're more accustomed with early in the subject. Depends how much practice you do with it, admittedly. But you can see that everything builds on, which is why people find this a bit harder. But just recapping, this n is the way to convert it. Replace the z's for the parameters, and then otherwise proceed as per normal, essentially. So you could have done this approach in all the previous cases too. So why didn't we? Why do we use the high-level theorems? So if you think back to this first one, is you're running over the sphere. You have, in order to work out the whole sphere, well, you have to split. If you wanted to try to use that approach, you either have to parameterize in terms of spherical coordinates, which you probably don't know very well, and therefore that's not to take you some time. Or if you don't use spherical coordinates, then you're really going to have to split the surface up into 2 bits, so the top hemisphere and the bottom hemisphere, parameterize in terms of x and y's, which you got to. I mean, just make z is equal to the positive square root and negative square root of whatever the rest of it is. That's the 2 parameterizations. and go and that sort of way. But the problem is you're going to square root and you have to take the partial root of that square root. You're going to get some yucky terms cropping up. And so it's the algebra is going to really blow out in that particular case, particularly when you have to start multiplying these square root sort of terms. With these ones here, it's really going to get quite complicated pretty quickly. And there's two parts to it. You have to do a top and a bottom separately. And indeed, if whenever you've got multiple sides, we'd have to integrate each side separately and parameterize each of them separately. It can really blow out in complexity quite a bit too. So that's why that one's a bad idea for this case, that you'd avoid if you can possibly help it. This one here, integrating over this paraboloid, well, this one is fairly similar calculations to what I did before, so it's doable, but if you did actually try it, you'd end up getting the same calculations anyhow. So it would reduce down to this particular integral as it so happens, because D here, it happens to be the shadow cast by the paraboloid anyhow, so it ends up being similar calculations. Okay, so that's the sort of standard approaches, and that is try divergence, that fails, maybe Stokes' theorem works in very special cases, and otherwise do the fallback of integrating by parameterization using this sort of approach. And so these sort of equations on the sample example formula sheet, so you can choose whatever you want to put on yours, of course, but that's a good one to have as a fallback position. But always be on the lookout for the other ones because that can save you time. So in your online assignment 4, which I think you've done, I was listening to me here, so Stig, you looking towards those high-level theorems can often make lighter work of it. But you can always fall back to things. What else? So, one more thing I want to mention. This is more an advanced technique. So if you have any questions you can ask first, by all means do so. Just want to look at one other way of doing this question. What do we have it? So it was, so we had this paraboloid, that's the black bit. It's a open surface, so you couldn't use divergence theorem directly, but what you could do is you could close it off. So you can add a little base to the bottom of it. So you had a little B for a base. In order to make the orientations work, we'd have to make it outward facing, so normal pointing down in this case, versus the top surface here with the outward, the normals pointing up. So we can close it off, so to speak. And so our paraboloid combined, so union with the base, now becomes a closed surface. And so the double integral of the combined bit would then be, by the divergence theorem, just summing over the divergence of this vector field over the entire volume. Now that integral may be worse than what we started with, but sometimes it is easier. So in this case, the divergence, if you plug it out, gives you 3. And then to work out the volume, you still have to do some integration, still a little bit of work, but let's just leave it for me, give you a bigger picture. So if that's doable, that's great. It still doesn't answer the question though. So the double integral of the flux through both bits together would be the sum of the fluxes to the individual parts. So that's the one we want, plus the other one we've sort of made up. So it's really the sum of these two. So this is our goal. So to work out this one over here, it's worthwhile thinking what it's going to be. So for this particular one, so because we've closed off, or we got full choice area closed off, we've made it a nicer one, i.e. something nice and flat. So we've chosen the normal to be facing down because it's in a plane. We can assure that the normal is going to be just a unit one pointing down. And because it's already in a plane, it's already in dx to y automatically. That's already taken care for us because it's in the xy plane. So you take the dot product of these two, you're getting minus the double integral of z dx dy. And again, like with all these sort of things, when you got z's different, we just have to just plug in the parameters. Well, in this particular plane, we know that z's 0. And so we're integrating 0. So this bottom integral here collapses to 0. So without having to do much work, we can at least, that one becomes nice for us. And so linking everything up, we can see that they're the same. That one's 0. So that these two integrals are the same. So what our goal is then can be reduced down to working out this triple integral instead. So the flux that we're really after is 3 times this triple integral of dz dx dy, and we're integrating z's from the bottom, z equals 0, to the top, 4 minus x squared minus y squared, and then integrating over the shadow, which we'll call b together. You integrate the z's, when you're getting 4 minus x squared minus y squared, and then dx dy, and then that ends up reducing down to integrating over the base, which is just a circle. And so then, just like we did before, we apply polar coordinates and go for that. And similar to before. So I won't do it. So not exactly the same, but similar. So is that approach any easier or harder? Well, sometimes it's much harder and not worth it. But this approach of closing off region using divergence theorem sometimes is nicer when it's easier to deal with the enclosed solid and the thing at the bottom. Or in an exam situation, this is coming from the sample exam, if you happen to have the integral of over the bottom already, so you already happen to have it, then that certainly becomes easier. And other examples, if the divergence 0, well, again, it's a good option for you. But these are trick methods which can help save your time if you need to. But if all else fails, close divergence, got a curl in there and use Stokes, and otherwise parameterize using x and y's is the should do it most of the time for you in an assessment situation. And that's true for your exam and your online assignment. That's what I'm looking for. Online assignment for. So I think I'll leave it there. There's a lot to this sort of aspect, and so it's worthwhile just letting it soak in. So if you've got any questions between now and your assignment or your exam, of course, just ask via email or the discussion board, as always, or make your phone call. I'm happy to do demonstrations of people individually online, so using desktop, just speak over the phone and share my desktop if necessary. You need to have a particular question in mind for it to make it worth your while, of course, but you can do those sort of things. Otherwise, good luck getting ready. Make sure you do your assignment 4, and please pay some time to do the evaluation. I find it helpful to hear what you think went well and what didn't go well, and what could be, how it can be improved. So thanks for attending. So there's a few people managed to attend live, so I appreciate that. Lots of people, I'm sure, watch the recordings based on the watching count. So thank you for watching as well. And hope I can see you you can stick around and maybe do some more subjects with us as well. But thanks very much. Any final words that you have, Stig? No, oh, that's awesome. So I'll stop the recording.